we're continuing on with Gauss's law. We're going to look at some examples today. We're going to try to use Gauss's law to find the electric field from a point charge, and Gauss's law to use the field from an infinite line of charge. So let's get moving. So again, here's Gauss's law written out here. And so it says for any closed surface enclosing some total charge Q, the net electric flux through the surface is equal to this. And so the net electric flux is this symbol. And we calculate it with this integral, and equals Q enclosed over epsilon naught. Again, epsilon naught is one of our constants, and this is known as Gauss's law. So obviously lots of questions about this. Like I said, this is really tough, so we're going to slow down and try to talk about it. What exactly is the meaning of an integral sign with the circle in the middle? So this integral sign here, is, so if you have some sort of Gaussian surface, here I made a Gaussian sphere, all right? So what you're doing again is you're taking this dot product, E dot dA, so like maybe some little tiny surface here, and you're looking at, the electric field vector might be pointing there, and then the area vector dA might be pointing there. You're taking E dot dA and then adding it up over this whole surface, and the closed little loop there means you have to do it over an entire surface. And we call this a surface integral. Last time I said that, for me, this was the first time I'd ever seen one. Maybe, when I learned about Gauss's law. For you guys, maybe you've seen one before. But it's this weird integral that's defined as being over an entire surface. And so we talked a little bit about this, calculated a few situations of flux, but really we should go through and do some examples. And the trick, or sort of the key here, is that this is super powerful in that sometimes I can say, well, I can look at this and say, okay, the total electric flux, I can look at that as either this really complicated integral, or I can also just sort of say it's equal to the charge enclosed over epsilon naught. And just a little hint, it'll be really rare for us to ask you to do some horrible integral. So when you first see something like this, try to think outside the box and think, okay, is there a way I can think about this in terms of just the charge enclosed? We're going to encourage you to think about that. We've had a few examples already, but just a little hint. Sometimes we'll use that integral, but we'll rarely actually have to do any hard integration. Just a sort of a tip. So here's a good example, a conceptual question. This is totally the kind of thing that could be on a quiz. So we have a spherical Gaussian surface, right? And so that's this region over here, right? This Gaussian surface is imaginary. It's a mathematical surface. And it surrounds an electric dipole. So our good old friend, electric dipole. It's nice to sort of be able to think about things we've used before. The net enclosed charge is 0, right? A dipole has a positive Q and a negative Q, so the total Q enclosed, right, for our Gauss's law would be 0. And so I want to know which is true about the electric field on our Gaussian surface. Is it 0 everywhere on the Gaussian surface? Is it not 0 everywhere on the Gaussian surface? And then whether or not the field is 0 on the surface depends on where the dipole is inside the sphere. And again, our sort of this definition we're talking about, we're just sort of, again, trying to get used to this. So it's this integral E dot dA equals Q enclosed over epsilon naught. So think about this one, and we'll talk about it. Okay, so I've asked this to students before, and so here's some student answers. So student A says, since the charge enclosed is 0, we can relate it to the equation Q enclosed equals E times A. In this case, Q enclosed is 0, thus EA is 0. Obviously, as we integrate the area, we simply get the surface area of the sphere, which would imply that E is 0. Thus, the electric field must be 0 everywhere on the Gaussian surface. So this is a common misconception, so just be real clear, this is not correct, okay, but that's okay, and you might have been thinking this too. Again, this stuff is super hard. And so here's another student. Because the net charge inside the surface is 0, the net flux throughout the Gaussian surface will be 0. However, this does not mean the electric field will be 0 at each point. Rather, there will be multiple E field lines which all cancel each other out and produce a net flux of 0. So again, conceptually, we think about the flux as how many electric field lines are coming out. And so basically, in this example, there'll be as many lines coming out as there are coming in. And so the total flux will be 0. But that doesn't mean the electric field is 0. So this is really tricky. And so I would agree with that person that B is correct. The electric field is not 0 everywhere on the Gaussian surface. And so let's try to unpack this a little bit. So here's just a kind of rough picture of this, right? So here's this idea of a dipole, like just like in that last case. And so if I draw this surface here, so again, I'm drawing my Gaussian surface, an imaginary surface here. All right, so what's happening is, again, the electric field is not zero at every point on there, but if you look, the electric field, so here's, over here there's some positive flux, right? Over on this side, there's some negative flux. And again, I mean, I sort of tilted the picture of a dipole, but the point is it doesn't really matter where the dipole is, right? If we draw this surface, there's going to be some lines coming out, some lines coming in, and overall, it'll equal zero. Okay, so our total electric flux, this thing here, equals zero. Now here's an example of, now if you actually wanted to do this integral, this is a nasty integral, right? You would actually, depending on where you put your surface, you would need a computer. You'd have to numerically integrate. You would not be able to do this analytically. It's a super complicated integral, right? And so it would be no fun, but because we have this clause over here that says, well, we know the flux equals Q enclosed, you can just look at this problem and say zero. All right, so this is a good example. So I think, first of all, it's really good just to sort of get this point here that the electric field doesn't have to be zero everywhere when the charge encloses zero. It's just that the total flux, the positive minus the negative, adds up to zero. But the other part about this is this would be a really great quiz question to sort of give this and say, okay, what's the net electric flux on this surface, right? And so if you're sort of not really good or sort of not used to Gauss's law yet, you might think, oh no, I've got to do this integral. How am I ever going to do that? But if you remember this, all right, you can just sort of get out of it really quick and say, oh, of course, that's zero. Right? And so this is, if you look at the questions we're going to ask, like there's one on discussion coming up this week, where if you think about the Q enclosed part, the problem is really easy. If you think about the integral, the problem is really tricky. And so we're going to try to encourage you to sort of think about it that way sometimes. Now here's a picture that just kind of hits home on this, again, this idea of a closed surface. So this, which is also what that student was asking about, when we do this flux integral, we do it over a closed surface. And so here's just a couple of pictures of some closed surfaces and the electric flux going through them. Just to kind of give you an example, sort of to show you how this stuff works. So the electric field lines are either going in or out. And you'll just notice one thing is that if we pick things correctly, or not correctly, but if we pick the right surfaces, like say in this example right here, so here I have a Gaussian surface, a Gaussian closed surface against some imaginary surface. It's surrounding some positive charge. If I put it concentric over that charge, the electric field is always 90 degrees to the surface. Okay, you can see that. Hopefully you can agree with that. And it's always constant over the surface. And so this is going to be what we're most interested in. Okay, we'll have examples like the one we just did. But this one will be something that can be really useful for us to figure out electric field for different kinds of objects. And to do that, we'll have to go back and reiterate this idea. So we talked about this last time. And so this is calculating the flux. Now you notice there is no, circle here. So here we're just doing like a surface integral that's not closed. And so we're looking at points. And so this is a point that's just like that sphere. The electric field is perpendicular to the surface and has the same magnitude at every point. This is pretty much the only time we're actually going to ask you to integrate this sort of stuff. And the thing is, it ends up being a pretty easy integration. Okay, and so again, the idea would be down here. You'd sort of say, okay, so I'd have my electric field times the, the magnitude of electric field times magnitude of my dA times cosine of my theta. And of course here, right, the idea is that since the electric field is perpendicular to the surface, so I have my surface, right, and so I'd have that, there's that area vector is always perpendicular to the surface. If my E field is perpendicular to the surface, then the angle between them is 0. So cosine of 0 is 1, and so that leads me to this next part, which is just the integral of E times dA. Now since E is constant, I just throw it in front of my integral. So I have E times dA, and then it's the electric field, and then it's just times the integral of dA is just the area, right? That's literally just going over my surface and adding up little tiny pieces of area, get the total area. And so typically that is that we can calculate in our head. And so what happens is we're going to basically try to find cases with symmetry where either the flux is just going to be equal to the electric field times the area, that'll be sort of our first case, or where the flux is 0. And we'll find that if we can find cases where we can do this, then Gauss's law can be a super helpful way for us to find the electric field for certain cases. Okay, so let's go ahead and try to do one of those and see what we get. All right, so continuing on, the key, let's back up. So the cases we'll be most interested in with Gauss's law will be cases where there's a huge amount of symmetry. And there's basically three kind of cases. There's spherical symmetry, right here, cylindrical symmetry, and planar symmetry. And so spherical is where basically there's no change if you rotate the sphere. Cylindrical there's no change if you sort of rotate around the sphere side, and then planar is no change if you rotate or sort of move it around. And so these would be the three cases. So we're going to be able to find the electric field in cases where there's spherical symmetry, cylindrical symmetry, and planar symmetry. And again, if you look at this picture, the idea of symmetry, you may have talked about this before, but basically it's a system where if you make the changes shown here in the picture, there's really no change to your system. And so the first case we're going to start with is spherical symmetry. And so the cases we're going to look at would be here a little point charge, and then a spherical sphere of charge. And so we've got sort of like we've cut pieces out of those. And you can hopefully see that if you have a point charge and a spherical grouping of charge that's constant, if you make your imaginary Gaussian surface, which since we've sort of got little cuts here, would be this little dotted line, the electric field works out to be that case where it's constant and 90 degrees to the surface. And so that's sort of our magic case. If we can find any case like that, then we can use Gauss's law to help us figure out the electric field really nicely. And so just to kind of hopefully sort of look at this picture. So here's my idea of a point charge. All right, and so if I'm trying to find the electric field right here, just to convince you that it should be pointing away from it. So here's like a point A and a point B. And so if I was to find the electric field from the point A, it would look kind of like that. The electric field from the point B would look kind of like that, roughly. And so, and actually that's a little bit off. Let me make that look a little bit better. Sort of like that there. So the total electric field points away from the charge. All right, and so that's how you can think about this symmetry, and it's going to work for a tiny point charge or a bigger spherical symmetry. And so this is the idea again. We're sort of making our Gaussian surface to be around here. And so this is kind of the magic point where the electric field is constant and 90 degrees to our surface. And that's what we really want in order to sort of approach these things. And so what we can do then is we'll start out with the simplest case, a point charge. Now we already know the electric field, but if you remember, we didn't really prove it. We just said, here it is. It was sort of like experimentally proven. And so this is a little bit more fundamental. We should be able to use Gauss's law. So here's the point charge. Here's my best attempt at a Gaussian surface around there. And what I'm going to call is the radius of that Gaussian surface is r. So in general, it's real important that you specify your surface or your radius. And so again, I'm going to say that the electric field, now I didn't really draw the best sphere, but I'll just go ahead and sort of draw this the best I can. The electric field is going to be at all points 90 degrees to this surface and constant because it's the same distance away. And so this is our sweet spot for Gauss's law. All right. So I drew that there. So we got this constant electric field, and it's going to be the same angle relative to your surface the whole time. So electric field is constant, and it's 90 degrees to the surface. And so my question here is this: E dot dA is equal to what? Well, let's do it. So we actually did this last time, but it's so important, I'm going to ask us to do it again just to make sure we're all on the same page. So on this case where there's a point charge and I have this Gaussian surface at some radius small r, what is the total electric flux through my Gaussian surface? And if you want, you can go back and look at this picture or this picture. They're sort of the same idea, but go ahead and try this one and we'll talk about it. Okay, hopefully you got this. C. So again, this is the case when that sort of sweet spot, when the electric field is 90 degrees perpendicular to the surface everywhere and it's constant, then our flux integral just equals E times A. And the tricky part then is figuring out what my A is. And well, here the A for this surface is 4 pi r squared. And so now here's our first sort of using Gauss's law to find something that we sort of care about. So I can say that the electric field times dA is going to be my electric field. Here I'll just use the magnitude of it times that 4 pi r squared like we were talking about. And then the trick is that equals Q enclosed over epsilon naught. And again, my picture just sort of, here's my Gaussian surface. And then I just had my little point charge in there. That's my Q. And so my Q enclosed in this case is just going to be the point charge Q over epsilon naught. And then what I can do is solve for my magnitude of the electric field. And if you go through this, hopefully you'll see and get Coulomb's law, right? So this is that sort of funny constant that we've been calling K, but it's the same idea. And so here we've found an equation that's a little more fundamental than Coulomb's law. And with it, we're able to solve for Coulomb's law. Now, when I first did this, again, like I said, I think this is tricky. And it's also like an example like this, it almost, you know, the math was, because it comes out to be, you know, just multiplying by surface area, it's almost too easy, if that makes any sense. And so this is really very conceptually difficult, I think. And so we definitely want to think about this. We're going to try to do some more examples. You know, the more examples, the better. You know, go through the book's examples, right? It's always helpful to see how someone else thinks about this. But again, just keep trying, and we'll get through this. Okay, so let's move on. So the next example we're going to look at is just the idea of a spherical shell. And so here's a picture of a spherical shell. And so now that we've done this, we've gotten this idea of Coulomb's law. You know, we already knew it, but we went through and solved for it. And so the thing is, if I have a spherical shell that's the same charge as this, so say this is a total charge Q, and say on my spherical shell I have a total charge Q. When you're outside of the spherical shell, Gauss's law is going to be exactly the same. Okay, so for this side of Gauss's law, you'd get E times A. Again, the electric field is constant. It's 90 degrees to the surface. And if the charge enclosed is the same, then what happens is for a spherical charge of size Q, I get the exact same thing. And so this is something that, you know, the book will sometimes talk about spherical shells. And where, you know, it's like, you know, it's sort of hollow inside or whatever. And in a case like that, right, it's going to work out that if you're outside of the shell, it works just like a point charge that was placed at the origin. So sometimes you have to be careful about this r distance here, depending on your problem. But if the book is like, you know, what's the electric field at some point P over here, right, it's basically just, you can just treat this as a point charge where all of its Q is at the center. And again, you can reason that completely with Gauss's law. So hopefully that makes sense to you. You know, which I think it's super conceptually rich, right? But sort of once you can sort of get it, it can be really powerful. So that it's the same sort of influence outside. Now, the other thing is that inside a spherical shell, right, you can argue. Like if I make my Gaussian, so here I've made my Gaussian surface inside the spherical shell. And so this is going to be a case where E dot dA equals Q over epsilon naught. And you can sort of argue this point, and that you can use this then, you know, to argue that the electric field inside a spherical shell is 0. Now to do that, you need to use sort of use the same sort of idea and just realize that the electric field at all points here again will be constant and will be moving in towards the center, just like we talked about before, right? And so in a case like this, you can argue that due to the spherical symmetry, it has to work out that same way. You can kind of think about it like right here, right? There's some charges on this side, there's some charges on this side, but they're all gonna, you know, they're sort of affect sort of left and right will cancel, and it'll all be pointing in towards the center. And there's no reason that any point is any different than any other. So just to reiterate, to make sure that that's clear, if I sort of, you know, pick a point right here, right, I'm going to argue that its electric field has to be pointing straight into the side. So there is some charge coming from the top here and some charge coming from this top, but the up and down y component will have to cancel, and it'll only have x component. And then since it's basically identical all the way around, it has to be constant. And so this integral here would again be e times a equals q over epsilon naught. And so that since there's no q enclosed, the electric field equals 0. So again, that would be really hard to do that by actually integrating. Right? You could treat this as like a continuous thing of charge and integrate like we did before. There's other ways you can do it, but with Gauss's law, you can do it just by kind of reasoning once this makes sense to you. So let's move on now to a new example. The last example we'll do today is the E field from an infinite line of charge. Now again, when you talk about infinite things, that's sort of weird, but we're going to talk about, basically you can approximate it in general with any kind of really long line of charge if you're really close to it. Okay, but let's say we've got some line of charge that's positive, for instance. All right, and what I'm going to argue, again, you can imagine that this thing goes on forever. I don't want to keep just drawing it, right? But I'm going to argue that at some point here, right, the electric field is going to point like this, right here. And if I look, what the sort of Gaussian surface that I'm going to try to develop will be a Gaussian surface like this. So it's basically a cylinder that surrounds this. Again, it's concentric to it. So the center of my Gaussian surface, this is my Gaussian surface. Again, an imaginary surface, a purely mathematical surface. Your calculus teacher would love this surface. And so it's this Gaussian surface, and it's centered on the wire. So basically the wire and we'll call the distance from the wire to my Gaussian surface to be r, and we'll call the length of this little Gaussian surface to be L, just for kicks. And so the thing is, you hopefully just want to hit home this point that the electric field on the surface of this cylinder has to be constant, right? It's the same distance from this charge, and it also has to be pointing exactly away from the surface, meaning, or from the line of charge, meaning that again this is 90 degrees, right? And so what that means, if I was to sort of draw here's my sort of line of charge down here again, at one point here, the E field points exactly away, right? So if I looked at maybe a point of charge here and a point of charge here, there would be some pieces going off to the side, but they're all going to have their X parts cancel and have only a Y part, sort of in that example there, right? So the key here being that the electric field is one of these magic points. The electric field is constant. So I'll say electric field is constant, because it's the same distance from the wire everywhere, so there's no reason that any other point is sort of more special than the other, and it's perpendicular to the surface. That's our magic sweet spot, that if we have that, then we can usually use that to find something out about the electric field from this particular object. All right, so here we ask, when do we have the E field piercing radially out of the side of the cylinder, and when do we have E piercing through the caps? And again, that's something that it's going to depend on your situation. And so this is, again, the really hard part, and it's the part that you really, it's hard to teach because you really just have to get some practice working with these different systems. But you need to look at each little system separately and then make this jump. Okay, here's my infinite line of charge. What would the electric field from it look like? And that's really the hardest part. Once you get good at that, then the math they're actually doing typically isn't that bad. It's more just realizing how it looks and how to set it up. And so let's try, now you guys have this, and I really urge you to stop here and think about this, because Gauss's law to me is like this classic example of where it's like, once you see someone do this example, it's like, oh, that was so easy, but it's not easy. And so I really want you to stop and do this. Okay, so the Gaussian surface we made was a cylinder. And so basically it's got what I'll call three sides. So it's got the two flat ends. So here's like one flat end here, and then the other flat end would be over here on this side. And so what I want you to do now is tell me what is the electric flux through the two flat ends of the cylinder, and I really urge you to stop and think about this before you let me give you the answer. Okay, hopefully you paused and thought about this. Last chance if you didn't, but it'll be 0. So if you look at those flat ends, right, if I was to draw one of those, so here's my line of charge, and here's one of those flat ends, the electric field on those flat ends is completely parallel to the surface. It's not piercing through the surface. There are no electric field lines going through that surface. So those two surfaces, the flux through them is just zero. There is no flux, right? And so like I said, we're going to be really interested in cases where the flux is either that simple case of electric field times area or where it's zero. And that's what we really like. So now let's do the other side. And again, I really urge you to go through and work on this here. So now, what is the flux through the wall of the cylinder? And so that would be my my third piece. So here's my third surface area. So we did the two caps, that was zero. What's it going to be through that third piece? And again, I really urge you to stop and think about this. Okay. All right, so I got B. And so let's look at this here. So again, what we're doing here to find the flux is this E dot dA, but this is the special case, and I'll go through it one last time just so we can kind of follow. So again, it's the electric field times my dA. There should be a cosine there, but the angle is 0, so it goes to cosine of 0. And then I can pull out that electric field, and then it's the integral dA, and that's just the area. So it's this case where it's electric field times area. And so now the trick is to figure out what is the area of this piece of the cylinder. And so what you've got is if I sort of cut this cylinder and light it out flat like this, okay, you've got a square, or one side of the square is L, and one side is the circumference of that circle, 2 pi r. And so my electric field, that's just the constant, so I'm just multiplying that times there, and then the area would be 2 pi r times L. All right, and so again, I'm not sure why we're going so sideways here, but E over 2 pi r L. All right, so now let's go through and see if we can figure out the electric field for this charge distribution. All right, so now we've figured out the electric flux through all the surfaces of our Gaussian surface, again our imaginary surface. And so from that, the only thing we got was E times 2 pi r times L. And now we equal to the Q enclosed over 1 epsilon naught. So our last thing is we got to remember that with a line of charge, right, we typically think about that as the total charge on there divided by its total distance. Now here, I used L for this here, so we'll just sort of say, like D is the total distance of this particular line of charge. I mean, it's an infinite line of charge, so it's kind of a weird thing to talk about anyway, but it will have some charge density, which we typically call lambda. And so the Q enclosed will be lambda times L, right? And again, that's just using our units, right? Lambda times L, this is, coulombs per meters, L is meters, and so that gives us units of coulombs, units of charge, and so that's how we would do it, right? So this length L is how much is enclosed. Now what's nice is here the L cancels, which is good because that was sort of arbitrary, the length of that cylinder we made, so that makes us feel nice, right? We sort of reason that our answer should not depend on that L, and it doesn't. And so when I'm all said and done here, I get 1 over 2 pi epsilon naught lambda over r is my, again, magnitude. And you can see what happens here is it goes as 1 over r. So Coulomb's law goes as 1 over r squared. This goes as 1 over r. And that has to do with basically the fact that it's an infinite line of charge. And so it's similar to what we were talking about before with the infinite sheet of charge. And so it goes off a little bit slower than 1 over r squared. This is something that the book calculated using the continuous line of charge integration. This Gauss's law is obviously mathematically an easier way to get there. As I said, conceptually, this is tough, but this is just another example of we can use Gauss's law to go through and calculate the electric field for different charge distributions. Okay, so again, keep reading the book, and we'll have some PCQs for this week. All right, thank you.